to make food healthier and more valuable. And it's not going to be easy because we're not all the same. Right? So the health requirements of one individual is not going to be the health individuals of everyone else. So we're now 16, 17 years into the 21st century. And the 21st century is increasingly dominated by the science of biology. And biology is not a reductionist science. Biology is an integrative science. It looks at complex systems, the complexity of individuals, the complexity of entire ecosystems. It recognizes, in essence, the complexity of living systems, and we're already beginning to see that biology is being industrialized. Right? From biological peptides Tona talked about, to if you bought yogurt this morning, you're paying to consume a living organism. So we're already beginning to see biology emerge. Chemistry is changing to becoming a science that supports this complexity. So no longer taking things apart and looking at the one thing that works, building analytical platforms to look at, in essence, the complexity of biology, accurately and sensitively. The big science, of course, is mathematics. Mathematics is transforming all aspects of science, and it's not the mathematics of the Greeks, it's the mathematics of big data. So we are now capable of creating massive databases and using computational methods to interrogate those databases in spectacularly fast and accurate ways. And you're all familiar with these technologies, GPS, Google Maps. It's also moving into health. So that's not an image. That's an NMR spectrum. It's an NMR spectrum acquired in a three-dimensionally oriented magnetic field, which means I can computationally reconstruct that spectrum to represent the three-dimensional space that it was acquired in. Now that is my heart. It's a fortunately non-invasive technique, didn't hurt, but the value is it's a data file. I can take that digital data file, send it anywhere I want. In fact, I did. I sent it to a colleague, friend of mine, Matthias Friedrich. He's a cardiologist. He can look at this data file in his own office, interpret it. Turns out I have a small scar in the upper left portion there where Susan Scott broke my heart in 8th grade. But being able to interpret this data means you, in essence, have delocalized medicine. And it becomes much more egalitarian. Becomes more and more cost-effective, and more people can take advantage. Of course, engineering. Engineering used to be the process of building bridges, massive installations to crack petroleum and soybeans, and increasingly engineering is the engineering of smart, small personal devices. All of these technologies are beginning to be leveraged to the problems of diet and health. And what we're realizing is diet's about to change. There is going to be a major revolution in the way people eat and the health that it provides them. There are three big drivers, three opportunities. I'll talk about the drivers first. It will become a knowledge-based system. Today, it's basically a system based on historic experience and culinary arts and a modern business model. It's conspicuously not knowledge-based. In essence, reflect the complexity of biology and the food materials. In order to understand biology, we're actually going to have to be able to measure it and understand it. And you're going to see that is actually coming now. And then finally, we're going to have to integrate that. We're going to have to make diet no longer a food that's good or a food that's bad, which is frankly a ludicrous idea. You are healthy or not because of the entire diet you eat. And if you don't get the entire diet right, there is no one food that will magically cure you. You have to get the entire diet right, appropriate to you, your diet, your lifestyle, your life stage, and that actually is what's coming. So, if food is becoming a knowledge industry, well, what does a knowledge-based system look like? You're all very familiar with exactly what it looks like. Google Maps. Right, now think about how much knowledge there is. Every street, every highway, every bike path, in the United States is in an accessible data cloud. The amount of data in that simple map is huge. And we have personal access to it in real time. And it's computationally appropriate. So it doesn't show you a map of the United States, it shows you the map of what you really want. It's dynamic, it's real time. It can tell you what the traffic is on the highway you're going to go on. It can predict the time it takes you to get there. And it's annotated in various ways, including the business model. Do you have to pay for Google Maps? No, it's free. Well, actually not free, someone pays for it. The companies that are providing access to where you're going to get your coffee, where you travel, where you're going to stay in a hotel, they're subsidizing the whole thing. So the business model is literally taken away from the consumer and moved to the people who have the most to gain. So this magnificent knowledge-based system in place today and working beautifully. So what's the value proposition? Where am I? Where would I like to be? How do I get there? And that magnificent system is working. So from a health perspective, what's my health status now? What would I like it to be? How do I get there? And then diet will guide us to that ultimate destination. What we're going to need is very comparable to the knowledge base of all those streets and highways and roads connected for what, in essence, they do. We're going to need to do that for food. We're going to have to build the knowledge library of food chemicals annotated for what they do to human metabolic pathways. So annotated for their functions. Now that sounds like an elaborate process, but we have been working on ultimately how people should eat, what diet does, and how we can integrate that. In essence, this complexity. And we use a very specific model. Tona's already alluded to it, biology, and the remarkable history of evolution. So the phylogenetic tree, all organisms, it turns out, we live on a microorganism world. There's no question. The vast majority of our organisms are still tiny microorganisms. We are a tiny little twig on a tiny little branch at the end of eukaryotes. But because we have the genomes of many of these stages of the phylogenetic tree, we have the entire genome. We have all the access to all the genes. And we can start asking very obvious questions. And the one we ask, what evolved under this Darwinian pressure of evolution to be food? To be nourishing and supportive, protective of the consumer who eats them. So when you take that approach, what evolved to be food, what you realize is, well, it's a war out there. And if we were to pick any selective pressure that has dominated evolution, it's the pressure not to be food. The selective pressure to avoid being eaten has been the strongest pressure throughout evolutionary history. And if you're, in essence, an organism that's still alive, you're good at this. If you're delicious and nutritious, you're gone from the gene pool. Right? Now, animals, insects, birds can fly away. Plants can't. So they have elaborated a very strategically impressive secondary metabolism to keep animals, insects from eating them. And that secondary metabolism consists of overt toxins, anti-nutrients, thorns and bark, and all sorts of ways to avoid being eaten. So, yeah, if you want to get rid of your major professor, the evolution of plants as food will teach you. What really evolved to be food? Lactation. This remarkable idea, very late in evolution, of the mammalian mother dissolving herself to make a complete and comprehensive diet for her infant. This mother-infant diet is a remarkable example of evolution of a food. Generation after generation, this Darwinian engine. If anything in the milk enhances the success of the infant who consumes it, it's hard to imagine anything that's under more positive selective pressure. On the other hand, of course, it's costing the mother, so if it's not good for the infant, it's going to be a loss to evolution just for the cost. So, I'll give you a quick summary of a story that we discovered while looking at human milk. We found something that wasn't there. So, when you look at human milk, take it apart chemically, one of the things you're struck by is how much completely undigestible matter there is. So, why would mothers make undigestible matter for a baby? So, answer that first we had to ask, what is it? Carlito Labriglia, head of analytical chemistry at UC Davis, one of the actually most brilliant analytical chemists in the world. He builds analytical platforms to discover complex biopolymers, and it turns out what milk is full of is sugar polymers, oligosaccharides, specific sugars in very stereospecific linkages, and there's 200 of them in human milk. And all of those stereospecific linkages between those sugars, babies have no enzymes to break them down. So as a result, they go right through the baby. So this seemed rather perplexing. Why would mothers make undigestible oligosaccharides to go through their babies? So that was our next question. I'll confess, I thought it was to feed bacteria. Right? If the baby's not eating it, something must, and bacteria made perfect sense. So again, we could enlist the help of David Mills, world-famous microbiologist. He studies the microbiology of everything from wine to the human intestine. We isolated the oligosaccharides, gave them to David. The bacteria grow on them? No. Broke my heart. He tries bacterium after bacterium after bacterium, nothing. Then he finds one. Oh, what a surprise, from the intestine of breastfed babies. And when you study the genome sequence of this bacteria, remember the oligosaccharides, very specific sugars in stereospecific linkage in human milk? In this bacterium are genes encoding the enzymes to break down every single one of those linkages.